This is the 17th video in a series devoted to ordinary differential equations, and today we're going to look at a family of differential equations that are called Euler equations. And we'll specifically look at second-order homogeneous Euler equations and see the strategy for finding all solutions to these types of differential equations. Okay, so let's look at our definition. An Euler equation is a differential equation of the form ax squared y double prime plus bxy prime plus cy equals 0, where a, b, and c are real numbers. And I guess I should point out here that a is non-zero. I won't write that, but just think that a is non-zero right here. So that means we, in fact, do have a second-order differential equation. Okay, so let's do a little bit of exploration to get started so we can get an idea for how we might guess a nice form for a solution to this differential equation. So let's note that if we take the derivative with respect to x of x to the r power, we get r times x to the r minus 1 by the power rule. But look over here, we've got the derivative and then a multiplication by x. So if we replace this with a new operator, which I'll call x d by dx, and attack x to the r, we'll just get we'll get r times x to the r. So the derivative will decrease the degree by 1, but then multiplying by x will increase the degree by 1. So in the end, we don't change the degree at all. And then we've got something similar going on with the second derivative. So let's notice that if we take the second derivative of x to the r, we'll get r times r minus 1 times x to the r minus 2 just by using the power rule 2 times. But if we kind of change this operator a little bit to put it in terms of what we have over here and replace this with x squared times d by dx, well, the second derivative, so x squared times the second derivative acting on x to the r, well, just like above, we'll end up with something with the same degree. And that's because the derivative will decrease the degree by 2, the second derivative, and then multiplying by x squared will increase that back to have the same degree. Okay, so anyway, here we'll have r times r minus 1 times x to the r. Okay, so putting this all together, let's maybe note that a good guess for a solution to an Euler equation would be something like this. Maybe we could have x to the r, so y equals x to the r for some real number r. And let's talk our way through that, why that might be a good guess. Well, that's because the second derivative only occurs when multiplying by x squared. So that means this object over here will be a multiple of x to the r. Likewise, our first derivative only occurs with a multiplication by x. So that means this term right here will also be a multiple of x to the r. But then if we start with y equals x to the r, that means the c times y will also be a multiple of x to the r. So putting this all together, we'll just end up with a multiple of x to the r over on the left-hand side of the equation, and perhaps that will help us out. Okay, so let's see exactly what happens here. So we'll have ay double prime plus by prime plus cy turns into a times r minus 1 times x to the r from our calculation right here, along with the fact that we're taking y to be x to the r. And then we'll have plus b times r times x to the r from our calculation right here, again with the fact that we're taking y to be x to the r. And then plus c times x to the r. Again, here it's just because we're taking y to be x to the r. Then from here, we can maybe factor an x to the r out of this, and we'll get r minus 1 plus br plus c. And then since the other side of this differential equation is 0, we need all of this to be 0. But this expression being equal to 0 must be true for all values of x, really all values of x in appropriate domain, in particular for x equals 1. So we could maybe set x equal to 1 right here, and that will collapse to the following polynomial equation. We have AR times R minus 1 plus BR plus C equals 0. And that actually motivates maybe an observation that we're going to start building over here. And that is that y equals x to the r is a solution to our given equation if and only if r is a root of this polynomial. This polynomial has a name. It's called the indicial polynomial. So let's write that, indicial polynomial. And so this might look pretty similar to when we had polynomials associated to second order linear differential equations with constant coefficients. And in that case, we had to split our result into three cases. The first case is if we had distinct real roots. The second case is what happened if we had a repeated real root. And the third case is what happens if we have complex conjugate roots. And in fact, the behavior of the roots of this polynomial pointing towards a solution of our differential equation of this form will also separate into those three cases. Okay, so let's get maybe our starting observation on the board, and we'll continue to add to it and then also do some examples. So far, we've motivated the first part of what is our big observation or solution strategy for Euler differential equations. And that goes like this. So the differential equation of the form up here, ax squared y double prime plus bxy prime plus cy equals 0, has a general solution of y equals c1x to the r1 plus c2x to the r2 if r1 and r2 are real numbers which are non-equal. So in other words, they are distinct real roots of our indicial polynomial. Let's recall that was the polynomial a times r minus 1 plus b times r plus c equals 0. And again, that follows from our exploratory calculations that we did previously. So let's apply this to the following example. So we have the differential equation x squared y double prime minus xy prime minus 3y equals 0. So what's our polynomial in this case? Well, the number a is 1, so that means that the first part of this is r times r minus 1. The role being played by b is negative 1, so that'll be minus r, and then the role of c is being played by 3. So this is the polynomial that we need to solve. So the standard strategy would be to expand this out. That'll leave us with something like r squared minus 2r minus 3 equals 0. And then we'll try to factor that. So since we've only done this first case so far, where we have distinct real roots, we should hope that this probably factors with distinct real roots, and it does. This thing factors as r minus 3 times r plus 1 equals 0. So that means we could take our root r1 to be 3 and our root r2 to be negative 1. So putting this all together, we have the following general solution. So c1x cubed plus c2 over x. Really c2 times x to the minus 1. So we have something like that. Now let's notice that this solution is discontinuous at 0. So the fact that this is discontinuous at 0 is really coupled with the fact that this function in front of y double prime has a 0 at 0. So in other words, if we evaluate this at x equals 0, we get a 0 for this very simple function here. But that means that our solutions only work on intervals that do not include that 0. So in this case, we could take this solution to be valid either on the interval from minus infinity to 0 or on the interval from 0 to infinity. So we'll take our interval of validity to be 0 to infinity for all of these. That being said, you can do a similar construction to get the interval to be minus infinity to 0. And in this case of distinct real roots, there's really nothing else to do. But that being said, if you're looking at repeated real roots or maybe complex conjugate roots, there is a little bit of work to do to write this on the kind of companion interval. I think that actually makes a pretty good exercise. Okay, so now let's go from this example to looking at the question of what happens if we have repeated real roots. So now we'll look at the second case, which is what happens if the indicial polynomial a times r minus 1 plus b times r plus c has a single repeated real root, which I'll call r1. So let's real quick notice that that means we can make the following factorization. So we have ar squared plus b minus a times r plus c. So that's what I get from expanding this left-hand side is in fact equal to a times r minus r1 quantity squared. So that's what it means for us to have a repeated real root, is that it factors as like a perfect square binomial. Okay, so let's notice that we know one solution already, and we know one solution from our exploration, and that would be y equals x to the r1, and we just have to find the other solution. And just to be real clear, we're still talking about a differential equation of this form over here. So how are we going to approach this? So there are a couple of ways, but the way that we'll do, not because it's most efficient, but because I think it's a really good time to review this technique, is to use Abel's Wronskian trick. So in other words, we're going to calculate the Wronskian by using the definition and calculate the Wronskian using Abel's method. So I'll call this Abel's Wronskian. And that will set up a differential equation because there's only one Wronskian for a differential equation. Okay, so let's first do it by the definition. So let's maybe color code this as a green dot, and over here we'll be calculating the Wronskian by the definition. So it's the determinant of the matrix made up of the solutions to this differential equation. So let's change our notation real quick and call this y1. That's our known solution. And then recall that this matrix is formed by taking those solutions and their derivatives. So let's put our function y1 right here. So that'll be x to the r1, and its derivative down below. So that's r1 x to the r1 minus 1. And then our unknown solution will be y. So I'll put y and then y prime below it. And this is just by the definition of the Wronskian. The Wronskian is the determinant of this type of matrix. We wrote this definition for a general n by n matrix earlier if you'd like to check that out. Okay, nice. Now we can take this determinant and see that we get x to the r1 times y prime minus r1 x to the r1 minus 1 times y. So that's one expression for our Wronskian. Notice it depends on the first derivative of y. And now we'd like to work through calculating the Wronskian using Abel's trick. So let's maybe color code that with this purple dot. So in order to do that, we really need to rewrite our differential equation slightly and do a little bit of work to get it maybe in the nice form. So let's take this and maybe divide by ax squared. That'll give us y double prime plus b over a times x y prime plus c over a times x squared equals 0. So that's our new differential equation. If you recall, Abel's theorem for finding the Wronskian required that the coefficient of y double prime was equal to 1. Then furthermore, in that theorem, we called this coefficient function for y prime equal to p, and in fact, the theorem said that w was the exponential of negative the antiderivative of p of x dx. So we could immediately write that down. That being said, I think there's a little bit of simplification that we could do before in order to write b over a and c over a in terms of our root r1, which is actually like a pretty achievable goal. Okay, so let's do that. So let's take this equation up here, this polynomial equation, and let's maybe divide both sides by a. That's going to give us r squared plus b minus a over a times r, and then plus c over a. So that's what we get from the left-hand side dividing by a. And then the right-hand side dividing by a will be r minus r1 squared, but I'll go ahead and multiply that out. So we have r squared minus 2r1 times r squared plus r1 squared. Okay, nice. Now we can equate coefficients. So the coefficient of r over here on the left must be equal to the coefficient of r over here on the right, and the constant term on the left must be equal to the constant term on the right. So that gives us this nice system of equations. We have c over a equals r1 squared, and then we have b minus a over a equals minus 2r1. But now let's take this b minus a over a and let's rewrite it as b over a minus 1 equals negative 2r1. And that's because that's a little bit easier to work with if we want to rewrite b over a. And our real goal here is to rewrite b over a so that we can put it into the Wronskian formula, and it looks similar to this Wronskian up here. So like I said, we can easily solve this for b over a, and what we'll see is that b over a is in fact equal to 1 minus 2r1. And likewise, c over a is r1 squared. Okay, so now that we've got that taken care of, let's maybe rewrite this differential equation using this calculation. So I've rewritten my differential equation really using the fact that r1 is a double root to our starting indicial polynomial and doing a little bit of algebraic manipulation. We ended up with the following setup. So by Abel's Wronskian theorem, we know that w should be equal to the exponential of negative the antiderivative of this function in front of y prime. But now we've got this function in front of y prime in a nice form to interact with the Wronskian when it's from the definition. Okay, so let's look at this. We have w is equal to the exponential of, so let's see, that minus sign can be brought in and make this 2r1 minus 1, and then we'll have the antiderivative of 1 over x dx. The antiderivative of 1 over x is the natural log of the absolute value of x, but like I said previously, we're looking at this on the open interval from 0 to infinity, so we don't need an absolute value. So this is going to give us the exponential of 2r1 minus 1 times the natural log of x. Now we've simplified something like this time after time, and the main strategy here is to use logarithm rules to bring this coefficient inside the log. That'll give us the exponential of the natural log of x to the 2r1 minus 1, but now the exponential and the log cancel and we get x to the 2r1 minus 1. So that's our Wronskian. So now that sets up a new differential equation from setting w equal to w. And that new differential equation is this purple underlined thing is equal to this other purple underlined thing, which if you look at it, that is a nice first order linear differential equation, which we'll solve now. So we just used our Wronskian equals Wronskian trick to find the following first order linear differential equation for our additional solution, where we used our previous observation and calculations to come up with our first solution earlier, and that really got us off the ground. So now I'll manipulate this equation so that it's in the format of a first order differential equation that we know how to just write the solution down for. So that will involve dividing by x to the r. So we'll have y prime minus r1 over x times y. So clearly the x to the r1 cancels, and then we're left with x to the minus 1 here, but I'll just put that in the denominator. And then that will be equal to x to the r1 minus 1. And now we'll just use the straightforward formula for writing down the solution. So we're going to need an alpha function. Let's recall that the alpha function is the exponential of the antiderivative of the function in front of y. So this is going to be minus r1 over x dx. That gives us the exponential of minus r1 times the natural log of x, which is x to the minus r1. So that's our alpha function. And then our final solution will be equal to 1 over alpha. And then we'll have some constant plus the antiderivative of the alpha function. So I'll just write this alpha function times our function b, which is the forcing function. So that's going to be x to the r1 minus 1. So something like this. So we had alpha was x to the minus r1, which means 1 over alpha is x to the r1. Okay. And then this will be x to the minus r1 because it's in the numerator. And then if we combine these two together, that'll give us 1 over x. We take the antiderivative and we'll get natural log. So in the end, we'll have x to the r1 times some constant plus the natural log of x. But let's notice that we don't really need to consider that constant because that constant is going to duplicate our first solution, which we already have. So that gives us a second solution of x to the r1 times the natural log of x. So let's rename this maybe y2. So now we have our first solution up here, our second solution up here, down there, which is x to the r1 times natural log of x. Now we can put this all together to a general solution of c1 plus c2 times the natural log of x times x to the r1. Because both of these have an x to the r1 as a factor, so we might as well factor it out like this. So that would be our general solution in this setup where we have a repeated real root. Okay, so let's get that on the board over here and we'll do an example. So I've added the summary of our previous calculation to our big observation for the day. And that is the solution to our differential equation is of the form c1 plus c2 times the natural log of x all times x to the r1 if r1 is a real number and it is a repeated root of this indicial polynomial. So let's look at an example based around that, and then we'll finish it off by looking at what happens if we have complex conjugate roots. So our example is x squared y double prime minus 3xy prime plus 4y equals 0. So we need to look at that indicial polynomial, like I said. So that'll be r times r minus 1 because our coefficient a is 1 here. And then we'll have minus 3 times r plus 4 equals 0. So let's see what we get if we simplify this. So we'll have r times r is r squared, minus r minus 3r is minus 4r plus 4 equals 0. So this factors as r minus 2 quantity squared. So that means we have a repeated real root of r1 equals 2. But now we just can write down the solution. So notice we'll have y is equal to c1 plus c2 times the natural log of x times x squared. And that would be our solution in this case. And if you recall, while we were doing our preparatory calculation, we made an assumption that we're working on the interval of positive real numbers. That's why we don't need an absolute value for the natural log here. And in fact, the last little note that I put in this observation when it's done is that these solutions hold on that interval of positive real numbers. Okay, so now let's explore what's going on with complex conjugate roots. So the last case that we need to cover is the case when we have complex conjugate roots to our indicial polynomial. So I've rewritten the starting differential equation here so that we have it because we're going to need to work off of this a little bit more hands-on than we did before. So whereas before we used the Wronskian, here we're going to use a different trick. And this different trick could actually have worked for all of these cases. That being said, I think it's nice to handle them all a little bit separately just to review material as we go. That's why we did this trick with the Wronskian previously. Okay, so we're going to start by making a substitution. So in that substitution, we'll turn this into something that we've dealt with before. So we're going to set x equal to e to the t. Thus, we're going to set t equal to the natural log of x. And I'd like to point out that this is okay because, just as I pointed out before, we're on the interval of positive real numbers, thus the natural log makes sense. And the exponential function is onto that set of real numbers. Okay, nice. And now we're going to set our function capital Y equal to our function little y evaluated at e to the t. So that means capital Y is really a function of t at the heart of it. And if you want to think about a functional dependence tree, we have y depending on x, which itself is depending on t. And we know how x depends on t by our substitution over here. Okay, nice. Now we're going to find the first and the second derivative of capital Y with respect to t using the chain rule. The chain rule will work via this tree, if you recall. Okay, so let's find the first derivative with respect to t. I'll use this dot notation on top to mean the derivative with respect to t. So just to reiterate, y dot means the derivative of y with respect to t. Okay, so that's going to give us the derivative of y with respect to x times the derivative of x with respect to t. So in other words, we'll have y prime times dx dt, but that's going to be e to the t times y prime, given that dx dt is just e to the t. And why do I have y prime here? Because y prime is exactly what we want. That would be like dy dx, if you will. Okay, so that's looking good. Now we could solve this. We could invert this equation if we wanted to, and in fact, we'll need that for our calculation. Let's note that y prime is equal to e to the minus t times y dot. So let's maybe keep that in mind. Now that's going to be super helpful because here we're going to replace these lowercase y's with capital Y's via this kind of inversion formula. Okay, so now let's calculate the second derivative of capital Y with respect to t. So I'll call that y double dot. So we need to use the product rule here. So the derivative of e to the t is e to the t, and then we'll have y prime. Then we'll have to take the derivative of y prime with respect to t, but we'll have to do that using the same sort of chain rule. So that's going to give us e to the t times y prime times the derivative of y prime with respect to t, which will give us y double prime times another e to the t because of the chain rule. So that's really by the same kind of dependence tree where we put a prime here, if you will. Okay, so now we can simplify this a little bit. This will be e to the t y prime plus e to the 2t y double prime. Another thing that I'd like to do real quick is notice that e to the t times y prime is in fact just equal to y dot from our previous calculation. So let's maybe erase this and replace it with y dot. But now let's look at this. We've got y double dot is equal to y dot, and then e to the 2t times y double prime. That allows us to solve for y double prime fairly easily. So y double prime will be equal to e to the minus 2t, and then we'll have y double dot minus y dot. Great. So let's maybe put an orange box around that so we have it. So there we've got y double prime in terms of capital Y prime in terms of capital Y, and plain old y in terms of capital Y as well. So let's rewrite our differential equation over here using these three orange boxes. So we'll have y double prime, which is e to the minus 2t, y double dot minus y dot, but notice e to the minus 2t times x squared is just 1 because x squared is e to the 2t. So that cancels. So that'll leave us with a times y double dot minus y dot. Okay, good. And then let's do the same thing for y prime. So notice y prime has an e to the minus t built into it, but this x is an e to the t. So those will cancel. That'll give us plus b times y dot, and then we'll have plus c times capital Y equals 0. Now we can move some things around if we'd like, and we'll get a y double dot plus b minus a times y dot plus c times y equals 0. And now in order to solve this, we can use standard strategies for solutions to second order linear differential equations with constant coefficients, because that's what we have. So that means we need to look at the polynomial associated to this, which is not the initial polynomial like it was before, because we don't have the coefficients of x anymore. In this case, it's the polynomial ar squared plus b minus a times r plus c equals 0. And it's b minus a because that's our coefficient here. But the trick here is that this polynomial can be rewritten as follows. We'll have a times r minus 1 plus b times r plus c equals 0. That's just moving this a times r over and then factoring the a out. Okay, but look, this is the initial polynomial for our starting differential equation. So it was maybe the associated polynomial to our differential equation with constant coefficients, but for our Euler equation, it was the initial polynomial. So that's the real trick here. So that means we have roots, I'll call them R1 and R2, as lambda plus or minus I times mu. Because that's our assumption, is that we have roots of that form for the initial polynomial. But applying facts from when we were working on our constant coefficient differential equations, we can write down a solution for capital Y. So capital Y will be e to the lambda t, and then we'll have c1 cosine of mu t plus c2 times sine of mu t. Okay, but let's recall that t was equal to the natural log of x. So if we put that in here, we'll have y is equal to e to the lambda times the natural log of x, but that ends up being x to the lambda. And then we'll have c1 cosine of mu times the natural log of x plus c2 times sine mu times the natural log of x. So it's kind of a gnarly solution. That being said, it's a solution that we can just write down given this special setup. Okay, so let's get that added to our observation over here and we'll do our final example. So we finished our observation. So if lambda plus minus I mu are complex conjugate roots of our initial polynomial, we have the following general solution. So it's y equals x to the lambda, c1 cosine of mu times natural log of x plus c2 sine of mu times natural log of x. And then all three of these solutions have interval of validity 0 to infinity. And you could get alternative solutions in each of these cases on the interval minus infinity to 0, which, like I said, is a nice little exercise that follows a similar strategy. Okay, so let's look at our final example, which is to find a solution to this differential equation. So as we've been doing for all of these, we need to figure out the initial polynomial. So in this case, it'll be r times r minus 1 plus 3 times r plus 2 equals 0, just from the parts. So that's going to end up giving us r squared plus 2r plus 2 equals 0. And then you can check that there are no real solutions to this by looking at the discriminant, which points us to looking at the quadratic formula. So we'll have negative b, so that'll be minus 2, plus minus the square root of, we have 2 squared minus 4 times 2 times 1, so that'll give us negative 4 in the end, and then this is all over 2. Okay, so the square root of negative 4 is equal to 2i, and then dividing the 2 out will give us negative 1 plus minus I. Okay, so that means we can write down our solution immediately. We have x to the minus 1, so that'll be 1 over x, and then c1 times cosine of the natural log of x plus c2 times the sine of natural log of x. And that would be our final solution here. Okay, so I'll leave you with some warm-ups. So I've got 3 warm-up problems for you, and as you might guess, they exhibit these 3 parts of our observation. So the first is 2x squared y double prime plus 3xy prime minus y equals 0. The second is 4x squared y double prime plus 8xy prime plus y equals 0. And finally, we have x squared y double prime minus 3xy prime plus 13y equals 0. And that's a good place to stop.